So after every lecture, you have a quiz and zip grade. So again, it's open for 24 hours and 6 questions. Make sure you do everything you can to complete those within the 24 hours. If you don't complete it, your score will be reported as a 0. Your exams are also in zip grade. So exam 1 will start on Monday. It will be open for 24 hours. It's 30 questions. You get 2 points, so it's worth 60 points. If you happen to miss that, those 60 points will then be tacked on to your final exam. So you may think, well, hell, I'll do none of the exams and then I'll just have the final worth whatever number of points. That's really not going to work in your benefit. So try to complete the exams when they're open. Shifting the points to the final is not a good strategy. The reason that these things are online, sort of outside of class, is that there's 142 students in here, and if people miss things, it's hard for me to keep track of. So that's why those things are shifted outside of class. Hopefully you have enough time to do that. Within that period, if you're sick or traveling or whatever, please try to make the time to make that stuff up. There's a practice exam that's in zip grade, so it's 30 questions, 1 point apiece. That's a bonus. So if you do miss the quiz or something, that will sort of backfill anything you missed. That's due tomorrow at 4. Again, Monday, you have both the lecture quiz and your exam, which are due Tuesday at 12. And then, so in terms of the grade, your letter grade, the only thing I really do is I type a grade in SOAR at the end of the semester. You earn your grade through accumulating points on these quizzes and exams. So again, it's in your best interest to do as well as you can. Any questions?
Yeah, so like I was looking at like the point chart and the syllabus, and I was getting so confused about it. So like,
So you're all familiar with the letter grade A, B, C, D, F, and then XF is due to academic misconduct. So from the letter grade, I set percentages of the total points. So all the quizzes, the exams, that equals some number of points. And then there's this percentage multiplier of those that you have to get whatever letter grade. So what's the percent of the points you need to earn an A in this class? 80. What is it for a normal class? 90. So that is a built-in curve, right? I do not curve in this class at all. The points you earn are the points you earn. They're not influenced by anyone else. So whatever the average on exam 1 is, that's the average. The points you earn are those points. That number is not going to change. So I'm not going to be bumping that up at all. So your bonus practice exam, that is sort of your curve in a sense. But it's 80, 60, 40, 20. Those are the percents of those letter grades. So, everyone in here can earn an A. It's just, imagine the 5 buckets. You're starting from 0 points and you're filling those buckets. So as you earn enough points to go past 20%, you're now in the D range, then you go to the C, the B, and then the A. So that's basically how the grades will work in this class. Any further questions on the exam or grading scale? Yeah.
how do you factor in those points?
So basically, let's say, for example, the class is worth 500 points. I don't know if that's the right number or whatever, but So you're earning a certain number of points. Say you get 350 points. Your bonus points will just add to that. So that'll bump it up to like 385 or whatever, 400. So the way it works is the total number of points for the class will not change. That's the denominator. Your numerator is your points plus the bonus points. That gets you your total points. Any chemistry material related questions before we start? So today what we're going to do is look at molecular formulas that are now incorporating nitrogen, oxygen, or halogen. And so once you stick that in the molecular formula, you can get other functional groups. So we'll look at the names of those functional groups and sort of the minimum number of elements that make up that word of the functional group. We'll talk about the influence of putting the heteroatom in the molecular formula. How does the melting point, boiling points change? And then if there's time enough, we'll do some examples where we take a molecular formula, determine degrees of unsaturation, and then we start proposing structures for it. So our first slide here, these are the nitrogen-containing functional groups. So CNOF. There's our abbreviated periodic table we need to know. So now we're going to stick nitrogen in. Nitrogen, remember, in the neutral valency, where there's no charge, always has 3 bonds in 1 lone pair of electrons, and that's what you'll see in these. On Monday, that's when we'll get into when things don't obey the neutral bonding pattern, and we have to calculate a formal charge. So that's coming up on Monday. So the first one is amines. And amines are derivatives of ammonia. So ammonia is NH3. And what we're doing, I'm going to use this word quite a bit this semester, is substituting. We're taking a hydrogen from the ammonia and we're substituting it for something else. So in general, that class of functional groups is called an amine. And you can classify the nitrogen as primary, secondary, tertiary, or quaternary. So you see the quaternary one has a plus charge. We'll talk about how you calculate that on Monday. So let's pay attention to this classification, because the rules for nitrogen are not the same rules for oxygen when we get to derivatives of water, H2O. So a primary amine, we can think of it as sort of 2 ways. We see the nitrogen. A primary amine has 2 hydrogens on it, and then it's bonded to 1 carbon. So really, in terms of the number, you're counting the number of carbons bonded to the nitrogen. So we see there's only 1 carbon, so that's primary. And again, keep in mind, nitrogen has 3 bonds. The lone pair, which is not drawn, it's still there. I just drew it in red. Secondary, now we can see there's a methyl group and then this other carbon, so that's 2 carbons. Tertiary has 1, 2, 3 carbons, and then quaternary, there's 4. And you're familiar with the term salt from general chemistry. So those are primarily what you've learned are inorganic compounds. So like sodium plus, Cl minus. So table salt, sodium chloride, that's a salt. That word also translates to organic chemistry. So I haven't shown it, but that plus charge would be balanced out by some other anion. And that would be called a salt as well. So you have a plus and a minus. We just generalize it. We call it a salt. So amines, you have a nitrogen basically with 3 sigma bonds to it. The next two functional groups, there's 1 degree of unsaturation in the presence of a pi bond. The first one is called an imine. So notice the vowel change from amine to imine, so there's A to I. And an imine has a carbon nitrogen double bond. So it is a pi bond between the carbon and nitrogen. The lone pair is still there. And then we see the 3 bonds. So we have the 2 sigma bonds and then a pi bond. So that's the 3 bonds, then the lone pair. An isomer of an imine is called an enamine. And so that is, any English majors in the crowd? Maybe not. A portmanteau, is that the right word? You jam 2 things together and make it one. So it's an alkene, which you can see from the carbon-carbon pi bond, and then an amine. And so that makes up the enamine. So there's the pi bond of the alkene, then you have an amine, so an enamine. And then moving up in degrees of unsaturation, 2 degrees of unsaturation is called a nitrile. So we have sp hybridized carbon, sp hybridized nitrogen. The nitrogen has that lone pair. So other words for this, a nitrile is also called a cyano group. So you might have heard of HCN, hydrogen cyanide. It's especially toxic. So nitriles are sort of derivatives of hydrogen cyanide, where the H has been substituted for a carbon. So here's a new term for us, heterocycle. So cycle, there's a ring, and then hetero means there's a nitrogen or oxygen. Halogens can't really form heterocycles. But the heteroatom is an atom in the ring. It's in that ring. So we can have 3-membered, 4, 5, and 6-membered rings. So due to the presence of the ring, those have 1 degree of unsaturation. And then finally, the last nitrogen-containing functional group are aromatic heterocycles. This word aromatic, if you're looking forward to or dreading Organic 2, you're stuck with me next semester. I'll explain exactly what that word means. But an aromatic cycle it has a ring plus pi bond unsaturations. So we have a 5-membered ring, that's called pyrrole. And then a 6-membered ring, it's called pyridine. So we saw with the hydrocarbons, you can have aromatic hydrocarbons. We've substituted out a carbon for a nitrogen. And we'll learn the properties of these as we progress through this semester in terms of how they act as reagents and acids and bases. So for now, we're just learning structure and functional group. Eventually, we'll learn their reactivity. So we have 1, 2, 3, 4, 5, say 6 nitrogen functional groups. Not to be outdone, oxygen has more, but let's look at this gifratoxin, which we talked about on Wednesday. And the question is asking you, looking at the nitrogen atom, how would you classify that amine? Primary, secondary, tertiary, or quaternary? So tertiary, let's identify the carbons. There's 1, 2, 3 carbons, no hydrogens, so this is tertiary. The reason it's important to be able to do this is because as we learn reactions, within those classes, primary, secondary, tertiary, quaternary, they'll react differently. So you identify it, it's amine, you classify it, and you say, okay, with this reagent, it's going to do this or that. So the oxygen-containing functional groups, CNOF, we said that oxygen has 2 bonds plus 2 lone pairs of electrons. So the 2 bonds can be 2 sigma bonds or 1 sigma bond and a pi bond. So you can have unsaturation. The first functional group are derivatives of water, where you've substituted just one of the hydrogens for a carbon. And so these are classified only primary, secondary, or tertiary. There's no quaternary alcohols. And so the alcohol must have the OH group, and then that's bonded to a carbon. So another word that you'll see in your textbook is called carbinol. That's the specific carbon of the chain bearing the OH group, which is also called hydroxyl. So alcohols have a hydroxyl group. The carbon bearing the OH only has one other carbon bonded to it, so that's primary. So that red carbon is only bonded to one other carbon, which I circled in blue there. For secondary, that's the carbonyl carbon. And now that's bonded to 2 carbons. So 1, 2, so that's secondary. And then finally, the tertiary has 1, 2, 3. And again, these things matter because that will influence the reactivity of the OH group when we learn about them. So now ethers, you've substituted both hydrogens of water for carbon. So the minimum sort of elements you need are carbon, oxygen, carbon. And so you look at the oxygen, it has to have 2 sigma bonds to carbons. So that's the ether. So carbon, oxygen, carbon. That's the ether. And a little bit later today, when we're going to look at some molecular formulas and say, okay, so what's the big deal between, the same carbon count of an alcohol with the same carbon count of an ether? How does an OH group affect the melting and boiling versus the ether? And we'll see that the alcohols have something that the ethers do not. So alcohols, ethers, now moving up to functional groups with 1 degree of unsaturation, where that's present in a pi bond. So a carbon with a double bond to oxygen, just those 2 atoms, is called a carbonyl group. And as we'll see on the rest of this slide, there's a lot of functional groups that contain a carbonyl group. And the way they differ is the things attached to the carbon. So in the carbonyl group, we've shown 2 bonds to carbon, but it needs 4, right? So you have these other groups coming off, and I'll just call them A and B. Whatever those things are determines what functional group name it is. The first one's called an aldehyde. And so we see the carbonyl group highlighted in red there. And then an aldehyde on one side will have a hydrogen, and the other side has a carbon. So the way you can think about it, the carbonyl group is at the end of the carbon chain. If you move it over to an internal carbon, now both of the things bonded to the carbonyl group are carbon. So carbon and carbon. And this has a different name. It's called a ketone. Any pre-health majors in the crowd? So when you learn about metabolism, you eat food, it gets metabolized. One of the byproducts of that is a ketone. It's called acetone. So 3 carbons. And so that gets flushed out through the kidney into the urine stream. Acetone is also nail polish remover. So that's the active ingredient in that. When I was a kid, my mom would paint her nails and then remove that paint with acetone. And I always liked the smell of it. It smells sweet, so it's nice to get a little buzz. Not for long though, but it's a sweet smelling compound. You might, in your 255 lab, you might make a compound that smells like bananas. So it's the essence of banana. If you like bananas, that's fine, but if you smell like pure banana smell, it'll get to you.
Is that how marker companies make it smell like bananas?
Yeah, they'll put different small molecules in there. So the other thing in grade school, you had the colored markers that smelled like fruit. You'd put it up to your nose or your friend's nose, and then you'd smack it, and they'd get like purple nose or whatever, but there's small molecules in there that smell like fruit, so a synthetic molecule. So moving on now, what we're doing again is changing the groups, the two groups bonded to the carbonyl. So 1 degree of unsaturation, these are called acid derivatives. So acid, as you're familiar with from Gen Chem, is like hydrogen chloride, HCl, or mineral acids. For this class, acid means a lot of different things. When we move into Module 2, we'll start defining them. And you're basically looking at the functional group to see what type of acid it is. Is there a question?
Yeah. So for the aldehyde molecule or degree of saturation, what's the 1 plus degree of saturation?
Oh, for the acid derivatives?
Yes.
As I go through it, I'll point that out.
Okay.
So a carboxylic acid has an OH group and then a carbon. What I want, so I'll highlight in blue. Those are the 4 atoms you need for a carboxylic acid. Sometimes students they'll read too much into that, and they'll call it like a ketone plus an alcohol. That's not a thing. When the OH group is bonded to the carbonyl, then it's a carboxylic acid. So it's a separate functional group. An ester, notice the difference between an acid and an ester. We've taken away that H from the acid and substituted it with a carbon that I've highlighted with a red dot. And so now that's called an ester. So small molecular weight esters, like the one you see on the slide, that's what's added to those markers to give them the fruity scent that they have. So when we get to, if you go to Organic 2, when we talk about color, how are things colored? Like this Gatorade is red. There's a molecule in there that's making it red. And it's red to appeal to your eye, so you drink it. I mean, it could be clear. It would taste the same. But we'll look at the influence of color on marketing and why you buy stuff. But small molecular weight esters, they're volatile. That's why you smell them. And they tend to have pleasing smells to them. The 1 plus that was asked about, the anhydride functional group has 2 carbonyls. So essentially what you're doing is taking a carboxylic acid, you're bonding 2 of them together. That's where the word anhydride comes, because formally you're losing a molecule of water when you do that. Anhydrides tend to be a little bit more potent smelling. So that the elements you need of the anhydride are shown in the red highlight there. 2 carbonyl groups joined together by an oxygen. And then the last one in this set is called an acid chloride. That has a carbonyl plus a sigma bond to a halogen. This just happens to be chlorine, but you can have acid bromides, acid fluorides, whatever that halogen here ends up being. You would just change to the halogen. So those were carbonyl groups that had either an oxygen or a halogen bonded to them. What if you have a carbonyl with a nitrogen bonded to it? That's called an amide. AMIDE. An amide consists of a carbonyl group bonded to an amine. So the carbonyl group, and then you have some amine. And we learned on the prior slide classifying amines based on the number of carbons bonded to the nitrogen. So that nitrogen has one carbon, the carbonyl carbon, so that's a primary amide. So secondary has 1, 2, that's a secondary amide. Tertiary has 1, 2, and 3. So there's oxygen heterocycles of different sizes, 3, 4, 5, and 6. We'll talk about the names of these things. You don't really need to know the names of them now. But they're used as reagents in reactions. They're also used as solvents. So solvent is typically defined as the liquid medium in which you run a reaction. And then one example of an aromatic oxygen-containing heterocycle is called furan. So we can see that it has 2 pi bonds plus 1 ring. That gets you your 3 degrees of unsaturation. Believe it or not, furan is actually present in corn. So if you take corn cobs and you boil it in acid, you can distill off furan. So this question asks, we've identified the hydroxyl group, there it is, this OH group. That's part of the alcohol. And how would you classify the alcohol? So it's primary. Remember, that is the carbonyl carbon. It's bonded to one other carbon. So we would get a primary alcohol. So keep in mind as we move ever closer to exam 1, that quote by the Nobel laureate Feynman, that the name of the molecule is gifratoxin, but everything we've learned so far, we've been able to describe more and more about this compound. We can count carbons, hydrogens, heteroatoms. We can classify attached hydrogens to carbons. We know about hybridization now. Now we know a little bit more about functional groups. So again, there's an alkyne, there's an alkene, we have a tertiary amine, a primary alcohol, and any other sort of CC or CH just within the molecule itself is an alkane derivative. Yep. For the prior couple slides today, when we talked about degrees of unsaturation, we're just talking about the minimum elements present to make up that functional group. When we're looking at the whole molecule, as we'll do a little bit later today, if we don't have the structure, we can just look at the molecular formula. But now the difference is those heteroatoms will influence the way we solve that. So halogens, halogens only form one bond, and then they have 3 pairs of electrons. So there's fluorides, chlorides, bromides, and iodides. They're classified according to the carbon that bears them. So this carbon is only bonded to one other carbon. The secondary has 2 carbons bonded to it. And the tertiary has 3. And so we saw in the prior oxygen slide, acid chlorides, that's when the halogen is bonded to a carbonyl group. So that's called an acid chloride or bromide or whatever the halogen is. Any questions at this point? Yes. For the aldehyde, you said? So for an anhydride, it has to have that, and then these other things, they can be whatever. No, then it's not an anhydride. So it has to be that specific arrangement. If you move that, so the question was if you move that carbonyl, so that's no longer an anhydride. This would be a ketone, and this would be an ester. So again, a lot of this is subtle, but just pay attention to the details. So here is sort of a culmination of those functional groups in a couple tables here. The first column tells you what the compound name is. The second shows you the structure. The third, the molecular formula. The fourth, the weight. Then the fifth and the sixth, the melting point and the boiling point. And so on the temperature scale in degrees Celsius, at the left, at 0 Kelvin, that translates to negative 273.15 degrees Celsius, so that's the coldest you can get. So if you imagine you start there, pretty much everything's a solid. And then this next sort of set of arrows shows you the phase transitions. If you're starting at negative 273 and then heat is added to the system, it's getting warmer. And so your phase transitions are going from solid to melting. So that's the melting point. It becomes the liquid. So there's a certain range where it's a solid before it melts. Then there's a certain range that it's a liquid before enough heat is added so that it boils and it becomes a gas. That's if you're adding heat. But then you can go the other way. you're taking heat out of the system. So a gas will condense back down to the liquid. The liquid cools, it will eventually freeze and then become a solid. So water, we're all sort of calibrated with water. We exist at 36 degrees. That's the normal body temperature. And then around 25 degrees C, that's room temperature. So again, if you're watching the news at 5, they're typically speaking in Fahrenheit, which are larger numbers. So in this class, we're going to use Celsius. It's a smaller number. So water calibrates us at 0 and 100. And so 25 degrees is room temperature. Our bodies are 36 degrees. So from negative 273 to 0, for those 273 degrees, water's a solid. And then it starts to melt, and then it's a liquid for 100 degrees. Then it starts to boil and become steam. So it has really nice, large ranges in which it exists in those phases. But I want to point out these two right here. Dimethyl ether and ethanol. They have the same molecular formula. They have the same molecular weight. But then look at, in particular, this number right here, 78. So ethanol boils at 78 degrees C. So, I mean, it's a liquid well above our body temperature. But then for the same molecular weight with a different functional group, dimethyl ether, that boiling point is negative 25. So it turns into a gas well before room temperature. And the question is, how can something with 2 carbons, 6 hydrogens, and 1 oxygen, that molecular formula form 2 different compounds with different physical properties? And if you look to the right of the chart, there's some terms here: dispersion, dipole-dipole, hydrogen bond donor, hydrogen bond acceptor. And so those are the reasons that these things have different physical properties. So in particular, you'll see that ethanol, with those 2 boxes shaded in green, ethanol is a hydrogen bond donor and acceptor, as is water. And so what does that mean, and why does it influence these properties so much? So I've written here this term NCI. That's non-covalent interactions. Let's just consider water. So H2O. So there's a molecule of water, and why does it boil so high? Again, think of what boiling is. You have this liquid, you're adding heat, and then molecules have to escape. So the heat is facilitating something to happen. So water is attracted to itself in all 4 of those ways. Dispersion. Dispersion is basically, sort of the electron cloud being perturbed a little bit. It changes a little bit. Dipole-dipole, if we had to draw a dipole for water, oxygen would be delta minus, hydrogen delta plus, And overall, you'd have this molecular dipole that looked like that. The dipoles can attract one another in terms of the positive end, the negative end. But what's really important is hydrogen bonding. So water is a donor and an acceptor. The OH bond, we've drawn it as a line, that's a covalent bond. Covalent means sharing. We saw from assigning the delta plus, delta minus, the bond itself is polarized. But there's also this non-covalent bond. It's a much weaker bond, and we'll explain the strengths of different types of bonds in Module 3. So if water is a donor, I'm going to highlight the O and the H. So it's donating that H so that another oxygen can accept it. And it accepts it through a lone pair. And I'll draw that with not a straight bond, but a dashed bond. And so that's called a hydrogen bond. And so all of the molecules in the bulk water do that. And it's an attractive force. So that is what the heat as you add to water is doing. It's breaking those hydrogen bonds to help the molecules escape and become steam. So ethanol can behave in the same way because it has an OH group. But we said this dimethyl ether, it has a pretty low boiling point. You can imagine dimethyl ether, we just substituted the hydrogens of water for carbons. So there's no longer H's bonded to the oxygen. So when the dimethyl ether is a liquid, it does not have the capability to hydrogen bond with itself. So that interaction is no longer there. So less heat is required to make it boil. If you've ever heard the saying, like dissolves like, so one of the things, dimethyl ether is a hydrogen bond acceptor. It has no OH to donate, but it can accept them. So you could dissolve dimethyl ether in water because it can accept the hydrogen bonds from water. So a way to draw that, so that's an acceptor. Water is a donor. Is the oxygen of the dimethyl ether can accept an OH bond from water. And so that sort of helps explain like dissolves like in this other term, miscibility. Does anyone like Italian dressing on their salad? So Italian dressing is typically oil and water. So we saw the structure of water. Oils are typically long carbon chains We call them fats. They're fatty. So fats do not dissolve in water because there's nothing that can sort of accept them. So as you learn the functional groups, you learn their names, start thinking about reasons why melting and boiling points change between functional groups of the same molecular formula. I think I'm gonna blitz past this slide. I'll talk more about it later on, because I want to get to this, where we saw hydrocarbons were alkanes, alkenes, alkynes. We used the CnH2n plus 2 to help us figure out what degrees of unsaturation were. But now when you start putting heteroatoms into a molecular formula, the rules change a little bit. And so there's 3 things you have to consider. If you have nitrogen or phosphorus, so I've just called it the nitrogen group, so going down that group in the periodic table, that will subtract 1. For every 1 nitrogen, it subtracts 1 hydrogen from your hydrogen count. The oxygen group, so oxygen, sulfur, does nothing. Your H count stays the same. Halogens, FCl, Br, will add. So nitrogen subtracts, halogens add. And that's pretty much what we need to know when we're given a molecular formula with heteroatoms. Can you picture in your mind what that structure gifratoxin looked like? If you have the structure, all you're doing is counting the pi bonds in the rings. That gets you your total degrees of unsaturation. But if you don't have the structure and you're given the molecular formula, you can still arrive at the same answer. So we're given C19 H29NO. Now we have to determine the influence of the N in the O on the hydrogen count. So oxygen does nothing. Nitrogen subtracts. So we revise that. The carbon count stays the same. So instead of C29, we have, or H29, we have H28. And then we're going to use that alkane formula for N equals 19. What, 40? Does that sound right? 19 times 2 plus 2. So for 19 carbons, we should have 40 hydrogens. We were given a molecular formula, we revised it. The carbons eliminate. We subtract 28 from 40. That gets us 12. A degree of unsaturation was defined as H2. So that gets us 6. And if you go back in the slides, I believe it was 3 pi bonds plus 3 rings. So that gets you your 6 degrees of unsaturation.
down front.
How would you know when to use
Say it again.
how would you know when to use H2N plus 2 versus just H2N plus?
What's your question? So the question was, how do you know when to use H2N plus 2 or to use like H2N? You're pretty much always going to use H2N plus 2 because that's going to tell you the total number of hydrogens you should have for 10 carbons. So we haven't seen the structure of efavirenz, but that's another molecule to help treat HIV/AIDS, and it has the molecular formula shown here. C14H9Cl F3NO2. One thing I do want to point out is it's always carbon, then hydrogen. Everything else is then listed in alphabetical order. Sometimes students, when they look at chlorine, Cl, they'll think that's a carbon and then an iodine. So your carbons are always listed first, and then everything else is alphabetical. So if there was an iodine in here, it would be between the F and the N. So we need to revise this. Oxygen does nothing. Nitrogen -1. Chlorine plus 3 fluorines, that's +4. So overall, we're adding 3 hydrogens. So we get C14H12. As a check, your hydrogen count must always be even, otherwise this will not work. So that's a check to make sure you're on the right track. So N equals 14. So 14 times 2 is 28, plus 2 is 30. That gets us H, 18. So that molecule has 9 degrees of unsaturation. So that's another skill you should be able to do. Given a molecular formula, determine the degrees of unsaturation in it. And we're going to run short on time here. We have about a minute left, but these sort of remaining slides are exercises for you to put this into practice. And just real quickly, let me get you started on this first one, and then you can see the logic of how to solve the rest of them. So the first thing we want to do is we're given C3H7Cl. Halogens add. So this will become C3H8. 2 times 3 is 6 plus 2 is 8. So this is fully saturated. There's no pi bonds, no rings. Now what we want to do is take that and just start drawing structures. So no pi bonds, no rings. We have 3 carbons. Let's just draw 3 carbons. And now we need to put a chlorine in there. So the best place to start is carbon 1. So there's one isomer. We can draw another where we put the chlorine at carbon 2. So that's another isomer. And that's pretty much all you can do for that molecular formula is 2 constitutional isomers. Now what you can do outside of time, we're running a little bit over, determine the unique number of carbons, unique sets of hydrogens, their ratios. You'll see that they're different. So there's more slides on this. You'll find that some of the molecular formulas will have a degree of unsaturation. And then the number of compounds for that, I mean, you could probably draw 25, 30, 40 different molecules that are constitutional isomers using all the functional groups we learned today.